If any of you can hear me, can you please respond audibly so I can check my volume?
I can hear you.
And the fact that I could hear you is huge because yesterday didn't work out. And I'm thinking it's Bluetooth on these headphones, connects to maybe a second device as well. But I don't know. Worked earlier. We'll find out. Okay. Hopefully your day is going well. How y'all doing? I'm going to take that as a thumb partway up or maybe a but where we're at right
I'm doing
now.
good.
Okay, excellent. Glad to hear that. So, and the fact that I could hear it is also good. So we're pleased about this. Um, okay, so I wanted to sort of start with the sharing of the screen thing because that allows me to sort of get into class mode. Before I do that, I don't feel like I'm in class. So class is now started. Okay. Just wanted to sort of like make sure we're all on the same page. Shouldn't really have to do this all the time, but I've found with some students, if I don't, there's a problem. So let's just go ahead and remember, oh yeah, there's a test today. Now, when I say today, what I mean is we're going to start the exam today, but it's due by Saturday, July 11, 11:59 p.m. Should not be a challenge to get it done by then because y'all can do the things. Okay. If you do end up with something unusual or surprising happening during the course of the exam or some emergency need beforehand, just let me know. The exam covers content in chapters basically think three, four, and five. The material that I yesterday talked about in chapter six, sections 1 through 3, that's due on Monday. Both the homework problems from chapter six, but also the lab activity related to the chapter six content, quality control or statistical process control, if you prefer to call it that, or Six Sigma is what some people also would call that. Our exam, I'm going to release it to the wild in about 48 minutes. And so that way, we're all on the same page. I thought it'd be a good idea to sort of spend time in class today talking about sample exam problems. Okay, so you could raise questions about these sample exam problems, assuming we get access to them. Yeah, so the sample exam two questions, or if you prefer, I did to some of the homework questions that were due yesterday. I put the answers online already, and they're built into the assignment. So you could just go into the assignment and look through the answers. But if you want to ask about any homework related questions, now is a good idea to do that. The content in chapter 5 is really the hardest chunk of material across the whole of the term for some students, and others like find it super easy. It depends on what you're like as a person, but typically I find that math skills don't mean you'll necessarily be good at probability. And sometimes it's the people who really like puzzles that find that probability is their jam. Okay. So with that in mind, I'm open to any questions or all questions that you might have because I want you to be ready for the exam, and this is the last opportunity to interact with me sort of in this context before you have to turn in the test. So any questions? Just unmute and go.
Can you explain like how we know when to use Bayes rules versus like the normal conditional equation?
Yeah, love it. Good, great question. So well, let's switch gears into that. Now I'm gonna make that smaller and just use the blank screen. And let's talk about Bayes rule versus regular conditional probability. Sometimes people talk about Bayes rule as tree reversal, if you will. We started a problem the other day, and I'm going to change the numbers up a little bit in the problem that we started, and then we'll use Bayes' rule to tackle it, and then I'll sort of get to answering your question very specifically. You in the UPS problem, we have some folks are pick a color. Is it even working? Okay, so now it should be working. If you have, okay, come on, yeah, undo that, do that. And where do we have this? Shoot. Okay, so we've got this is goofy the way this is looking. I'm sorry. Uh, okay, so the Apple Pencil is not working really well. In fact, maybe isn't working at all. I'm gonna just oh, I think I figured it out. Just a moment while I reconnect the pencil via Bluetooth. I apologize for this. Mhm. Okay, Bluetooth. And that's all. Okay, so the pencil now should be working. And I was just being a bonehead earlier. Okay, so here we go. Um, if it's not working now, that's going to be pretty funny. Okay, so some folks are using marijuana, others are not. So I'll call that M prime. And then some folks will test positive and some will test negative. And I don't know that this is the exact way that we had it last time, but positive and negative, I'm going to have positive on the right. And we said 0.05, 5% were users, 95% were not. And if you are using, and then the chance that you're going to test positive, I said was 99% in 0.01. I'm going to change it up a little bit, and I'm going to go with 98% of the people who are not using will test negative, but 0.022% will test positive anyway. I don't know how that would happen, but let's work with these numbers. Last time I had them as 0.01 and 0.99, and that is not what I want to go with because I think the choice of different numbers will clarify. It'll make it easier to follow the problem. Okay. So I'm going to tell you probably that someone uses is 0.05. Okay. And I'm going to tell you the chance that you test positive, given that you are a user, is 0.99. Okay. And I'm also going to tell you the chance that you test, I'm going to usually say negative, given you are a non-user. That's 0.98. Okay. Those would be a base probability and two conditional probabilities based on which branch down the tree you went. The Bayes rule would typically be utilized whenever you end up with something like this. What is the chance that you are a marijuana user given you test positive? That's the question that UPS has. Of the fraction of people that test positive, what fraction are actually using? That might also be a question that a individual in prospective employee who might have tested positive falsely would want to know because you then say, well, but dude, you're going to test a lot of people, and there will be a fair number of false positives. So, if you're given probabilities that look like that, and you want to switch the order of conditioning, that's exactly when you would use Bayes' rule. I don't really like to think about it as Bayes' rule per se, but just as an application of conditional probability, or even well, let's work from the definition. This is the probability that will equal the probability that you are a user and also that you test positive, divide through by the chance that you test positive. Yeah. And well, the user and test positive, that's going to be probability that you are a user times the chance that you test positive given that you are a user, that's our M for marijuana user. Okay, and then there's two ways of testing positive. There's also these guys over here off to the left, which are going to be M prime and positive given M prime. Okay, so in the denominator, you've got, well, a repeat of the numerator, M times probability of positive given M. Plus then, well, shoot, there's the people who are not users, but some of them will test positive even though they are not users. Close parenthesis. Okay, maybe I made a square brace. Okay, so there we go. Okay, so that looks like Bayes' rule. If I just replace the M's with A's and the pluses with B's, it's going to look exactly like what we saw in our textbook. Okay. The upshot really is you're going to find the numerator divided by the denominator, and that's from the definition of conditional probability. And then in the numerator upstairs, you're going to have just one product, and it's a conditional product, and it's instead of M given positive, it's going to be positive given M times the chance of M. And then in the denominator, you're going to see multiples of that thing that we saw in the numerator. It's just the other items will be covering the other case. So Magda, I think I answered your question, but that's up to you. Do you want me to rephrase or do you want to follow up?
No, I think I understand now. Thank you.
Yeah. Anyone else? Because Bayes' rule is sort of a tough one, but its use is usually easier to see when you do it from scratch. Like I was saying, oh, well, just write it out what you need. And then say, here's how we could get that. And then sub in where you need to for the numerator and denominator terms. And you're going to end up recreating Bayes' rule. If you attempt to memorize Bayes' rule or Bayes' theorem and say, well, I have to remember how to do this, it's going to be harder than if you just write down the basics and then plug in where you go. Okay, good question. Anyone else for a question in general or about class from 2 days ago, or let's just say probability homework questions in general?
Is there a
Okay.
specific composition of the exam that you have like thought about, or
What
will
do you
you
mean
already made it?
composition?
Like how many questions, like XYZ?
Um, no, not really. But if you remember the last one, it will look and feel sort of like that. There will be some questions where you're asked to provide a number. In this case, I set up a couple of them to be auto-graded, where you have to get the number right, but I gave a fairly wide tolerance for people who maybe made small errors. And then you're always welcome to sort of like if you see more points were marked off than you wanted, you can just let me know. Hold on, what I did was right, and I could look at it again. But a lot of short answers, and about the same amount of time. Yeah. Jose, does that get to your question then?
Yes, thank you.
Someone else maybe. Okay, seeing no questions currently, I'm going to go ahead and delete all that and then switch gears back into the sample exam because I find that when I just start to go through things like the sample exam, someone will invariably say, hold on, well, what about this? And they end up asking a great question. Okay. So that's probably what I'm gonna do now. And if you decide you have a question, even if it's not like right on the thing we're talking about at the moment, that's great. Ask away. Okay, so rolling a fair die. A one or a six, those are sort of the fun outcomes in a die, if you will. Um, I don't know why, but let's just say that that's things you care about. Uh, and if X is just the number of rolls, that sounds like it's a probability distribution or a random variable. Literally, there's an infinite number of possible outcomes. It could be 57,416. It's probably not going to be that high, but we'd have to keep going no matter what the value is for X that I could choose. We could sort of go with it. And so I'm going to list off the first roll. We'll get you a one or a six with a chance of 1 and 3. The second roll with chance 2 9s. How would that happen? Well, you have to get sort of a not a 6 first, which has chance 2/3. And then you have to get a 6 or a 1 on your second roll, which has a chance 1 and 3. So it's going to be 1 and 3 times 2 and 3, 2 9s overall. Or 2 9s, I mean, sorry, 2/3 times 2/3 times 1/3 will get you 4/27, or 2/3 times 2/3 times 2/3 times 1/3 will get you 8/81. Here is the probability distribution, and it is a random variable because if I ask you to do that, you can't know the outcome in advance, but X is a number. Okay, there you go. That is the definition of a random variable. So 3 or fewer rolls. Oh, that's going to be pretty quick because 3 or fewer is these 3 chances added up. That's going to be easy. What's the chance that it's more than 3? It'd be 1 minus the chance that it's 3 or fewer. So instead of adding up an infinite number of terms, you could add the third, 2 9s, and 4/27s, subtract the sum of these 3 shaded ones from 1 to get the chance of more than 3. Okay, so you got these two buddies, A and B, and they're going to play the game separately. And their outcomes, one will get a number, the other will get another number. Maybe it's even the same number, but they're going to have their separate outcomes. Would Ollie's outcome impact Beatrice's outcome at all? No. It's going to be independent. Independent. The definition of that is the chance, of Ali's outcome, okay, doesn't depend on Beatrice's outcome, period. No matter what you know, the chances are gonna then multiply if you want to use those up. Use it that way. Mutually exclusive. The reason I put that in there as the alternative, it's either independent or mutually exclusive. Sometimes people get stuck on the words. Independence, some students think, oh, has nothing to do with. Mutually exclusive, some people think, oh, has nothing to do with. No, 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 no. Those are definitely different. Independent means the chance of the one doesn't depend on the other's outcome. Yeah. The conditional probability is the same as if I don't give you the B outcome, A is going to either happen or won't. Okay, so what's the chance that both of them have 3 or fewer rolls? Well, if we found the chance of 3 or fewer, the chance, if you said independent, you're going to just multiply your answer in part B by itself. Okay, so it's going to be the answer to B squared. What's the chance that at least one of them would have 3 or fewer rolls? Well, okay, hold on. The logical opposite rule, the 1 minus rule, that's what I would turn to first. If I was sort of thinking through this part E and I said, that's not easy, ask myself the following question. If I phrased it as the logical opposite, would it be easier? So the logical opposite of at least one of them has three or fewer roles. The logical opposite of that is neither has three or fewer roles. Both have more than three. And we know the chance of more than three. Okay, so if your answer for part B, I don't know the answer to part B, but let's suppose it was. I'm going to call it PB. Yeah. This is going to be PB squared for part D. For part E, it's going to be, well, neither of them can have a three or fewer. At least one. Okay, so one minus the chance that neither of them has three or fewer. So it's one minus neither having three or fewer, and not having three or fewer is one minus PB. And then I'm going to multiply that by one minus PB. So both of them have four or more results. Okay, any questions about this first problem? Okay, I'm going to clear that and then head down a little bit. Okay, so what's the question in 2A? If you know that at least one of them has three or fewer, what's the chance that both of them have three or fewer roles? Okay, if you know that at least one of them had three or fewer roles. Okay, how do I think that one through? Okay, I guess I could draw a tree diagram. Okay, so I'll leave first, three or fewer, and I'm going to go with L for less than three, not L for more than three for Ali, and then Beatrice, L or not L, and then L or not L. So we could take that approach. Okay. And I could sort of list off all the ways that at least one of them has three or fewer, and that's these three here. The probability that, and what is the question again? What's the probability that both of them have three or fewer roles if at least one of them has three or fewer roles? So it's really the question, what's the probability that we have an L followed by an L, if you will, the event LL, given I'm not an L prime L prime prime. Oh, that's horrible notation. Let's redo that entirely. Okay. We are not, I'm just going to write it out. Not L prime L prime. Okay. And so I guess I could, the conditional probability says write out the numerator. So that's well, the intersection. So the probability that you are an LL or sorry, LL intersect, not L prime, L prime. Okay, so it means you're a this, or I'm sorry, and you're also that, over then the probability that you are not L prime, L prime. And in this case, I'd say, well, that's only going to happen if you have an LL, you are lower than four, and then lower than four, three or fewer, I guess, over the chance that you're not an L prime, L prime. So that's a one minus probably of LL plus probably of L prime plus the probability of L prime L. So I guess that is one approach I could take. Hold on a second. No. I'm sorry. That is not involving a one minus. There it is. If I wanted to use the one minus rule, and that will simplify things, that's P of LL over one minus P of L prime, L prime. Okay, so two ways to get the same answer. That's how I tackle the problem. Answers on this question were pretty good on the test, by the way. Okay, so let's clear this. Hopefully I can clear this. There we go. Clear the drawings. You get back to the sample exam. Okay, so using notation like so I guess I could literally ask you to just write out A1, A2, A3, A4, A5, then B1, B2, B3, B4, B5. Yeah. So how could I have the average less than or equal to 2.5? I guess A1, B1, or the average would be 1. A is 1 and B is 1. The average is 1. A1, B2, A1, B3, A1, B4, A1, B5. Hold on a second. That would not work. A1, B5. That's yeah. Okay, so we could list off all those possibilities. Okay. And we could find then that chance. Could we not find the chance? We could definitely find the chance in part C. So I'm going to sort of tackle this problem by saying, well, A gets a 1, and B gets a 1, or A gets a 1, B gets a 2, a 1, a B 3, A gets a 1, B 4, and that would be a total of 5. So the average would be 2.5. A 2, B 1, A 2, B 2, A 2, B 3. Okay, that also would have an average of 2.5. A 3, B 1, A 3, B 2. And then a 4B1. Here's all of the possible ways, all 10 ways that we could get the average being 2 or fewer. And I guess if I wanted to find, for example, one of these chances, let's go with this guy, I could just read it off the table because it's going to be the probability that A is 3. So I'm going to write that the chance of A3 times the chance that B is 2. And they're each from our friend, the probability distribution. A2, that's 2/9, and B3, that would be 4/27. So this is sort of something that could be done. I think the thing that took some people a little while on the exam is to write out all the ways. But once they wrote out all the ways, then they said, okay, yeah, I could find the chance. But it takes a little bit of time. Some people answered for 2C. They answered, oh, the probability distribution isn't normal. And we can only find the chance that the average is in a certain range if we have a large sample size or a normal population. So we can't do it. That answer was showing some memory of what we call sometimes the central limit theorem, that if we have sampling from a distribution that isn't normal, indeed a large enough sample size will get us the ability to find approximately that chance. But just because we can't use the central limit theorem, because n isn't like 25 or 30, doesn't mean in a case where it's like 2 and you can list off all the possibilities, you can't do it. You definitely can do this. Okay, so I guess for for question 3, I'm going to sort of want to sort of focus on, the 6 people, what is the chance that the average result is less than 3.5? Well, we could consider the question, and here's how I would probably do this if it were myself. I would write some code in R, and I would say, I'm going to randomly have 6 people sample from this distribution. And I'm going to find whether the result is less than 3.5 or not. And I'm going to just run the simulation for 10,000 times or so. And the definition of probability is the long run ratio of times that this happens, that the 6 would average 3.5 or less. The long run ratio of times that happens to trials. So I'm just going to keep track of successes where like all 6 had the average being 3.5 or fewer versus failures. I'm not going to ask you to do that on a test, to write code and to sort of do that. So a reasonable answer here on 3A is to say, unlike where, 2C where we can do it, in 3A, this probability probably can't be done in a closed form with an equation. Yes, I could conceive of someone write out an equation, but I'm saying that's not what I would expect. Okay. Yeah. small sample size from a distribution that isn't normal, we can't find the chance that the average is going to be in a certain range. However, if it's a large sample, 96, could we do it? Yes. The distribution of the sample means follows a normal curve if the sample is large in size. And so you need to know the average and the standard deviation of that distribution. Did we know that? Oh, mu is 3 and sigma squared is 6. So we know the standard deviation is the root of 6. So I think I'm in good shape. I could do problem 3B. Anyone want to talk about 3B? Or anyone want me to talk about 3B? Okay. So here's why I love question 3C. Question 3C says, yeah, you might not have been able to calculate your answer to question 3A, but you still should have a gut feeling whether it's bigger or smaller. Here's how I'm going to sort of approach it. One thing you remember from our discussion of that central limit theorem or a large samples, the distribution of the possible. If n is small, and I'm sort of going to sort of sketch it out schematically, is like, okay, so if n is big, indeed, we're going to have a narrower distribution of possible sample means. If the sample size is large, we've got things tighter around. And if you remember, that was 3 right here at the average. 3.5 would be a little bit above the average. And no matter how far above the average it is, if we have a narrower distribution because n is bigger, we have a smaller chance. And so my thought is for n of 96 and n of 6, we could approximately say, yeah, for the larger sample, the chance would be lower. Questions about the concept? Okay. So question 4 is really, it's looking to me as though it's going to be a natural use of Bayes' theorem or tree reversal. If I tell you of the people who got a low draft number in 1973, 21% were Democrats, 67, and then 12. Of the high draft number, it's a little bit lower for the Democrat, a little bit higher for the Republican. It's almost as though whether you were drafted or not impacts who you vote for. And that's the nature of the problem. They asked a group of people who had low draft numbers who were unlikely very likely to be called up in the draft. The lower your draft number, the sooner you're going to be called into the draft. Higher draft number basically says you're not likely going to have to serve in the Army in Vietnam. And so question gets after, well, can you tell me even in words what these things mean? Yeah, can you tell me what this is? So I'd say the chance that you're a Democrat, given you got a low draft number. Similarly, I could have asked about the chance that you're Republican, given you got a low draft number, or Democrat, given a high draft number. Okay. So overall, we see in the upper right corner, a lower right corner, 19% here. Yeah. What does that mean? What does that mean? Well, within a row here, we're given conditional probabilities. Given your low, yeah, what's the chance you're a Dem, Independent, or Republican? Given your high, Democratic, Independent, or Republican. So we're given those conditional probabilities. We have a, well, it's the lower row, so that's given high. So that's Republican, given you have a high draft number. This question really is my attempt to say, can you understand the difference between the and, the or if you will, the intersection and the union, and the two possible conditional statements? You know, it's high and Republican. Is it high and Republican? High or Republican? Republican given high, or high given Republican? Okay. Find chance of Democrat given low. Well, hey, that one's given to you. So pretty much everyone on the test got that one. The chance that you're a Democrat, that's going to be hard to do. That's going to be hard to do because there's two ways of being a Democrat. So let's switch gears a little bit. The probability of Democrat is, again, in a tree, we are given low draft number or high draft number, and then there's either Democrats or there are not D prime, D or D prime. And so we're given the probability of Democrat means, well, you're either that way or you're this way. There's two mutually exclusive ways of becoming a Democrat. You got a low draft number and you are a Democrat, or you have a high draft number and you are a Democrat. And low and Democrat corresponds to you have a low draft number, and then also you're a Democrat. So that's probability of low times the probability of D given low, plus then high times the chance of Democrat given high, D given H. If we then continue on with the question, okay, the chance of Democrat there. How about low given Democrat? Well, that is low given Democrat. Let's write that out. The probability of low given Democrat is the probability of low and Democrat over the probability of Democrat. And we just calculated that one. And so I'm going to have the probability of low divided by what I just calculated above. I'm sorry, low and Democrat upstairs. I apologize. Let's actually do this correctly. Okay. Probability of low then times the probability of Democrats given low over then what we had just calculated earlier. Okay, that's what I'm going to stick with. Okay. Do that. So low given Democrat, and then hey, here are actually there's no particular right answer here, but there are a variety of answers that are all pretty good. So if you're personally shielded from participation in the Vietnam War, does that change your politics? We could say, is the probability of Democrat different if you have a low draft number than if you have a high draft number? You could also say, is the chance of Republican different if you have a low versus if you have a high draft number? So these two comparing, or those two comparing, would both be quite reasonable. I've seen other student answers that convince me the student's got it going on. Okay. What about the last topic that we haven't touched on yet? Oh, regression. Yes. And here's a fun data set from history. And it literally is a place where you can go online and bet on next year's breakup in the ice flow. Yeah, so this one river, Nenana, the Nenana River that goes through the town of Nenana in Canada. Nenana is a student from Alaska corrected me, not Canada, Alaska corrected me, and said, "Oh yeah, this is definitely a thing." And you can literally go to the website and bet on to the nearest minute when the ice breakup occurs. So they sort of go and set up. They used to set up like a pole at one end and a pole at the other side of the river, and stretch a rope across it. And then they had a thing anchored into the ice. And when the vertical bar that was anchored into the ice went past where the rope was, went and touched the rope, they said, okay, officially, the ice is broken. Okay. They might do it with lasers now. I think you could. But the real thing that's cool about this is we have data on how many days, or alternatively, how many minutes. If we measured it in days or in minutes, it just doesn't really matter. It's just a matter of scale. Okay. We measure it usually in days, and a fraction of a day means, well, like 100 days plus a half is going to correspond to 100 days plus then noon. Yeah, you go half a day. Okay, so it's breaking after midnight of December 31st. That's how we're measuring Y, and X is how many years has it been since 1900? So like the 100 there, that'd be the year 2000 is where we got this data point. Okay, so R squared here, we saw in regression. Yeah, R squared, easy to read. Can you explain it? And R squared is indeed the proportion of variability of the ice breakup dates that could be explained by how long it's been since 1900. Okay. Uh, how much variability is there in the actual breakup dates relative to the predicted breakup dates? Okay. How far away are the individual data points away from the trend line? Root mean square error is the number that describes that, RMSE. Okay. You could also talk about the sum of the squared errors around the trend line. But yeah, literally the square root of mean square error is root mean square error. And that's the number we would use to talk about how far off we are. Like if we're going to try and predict for next year about how far off would you be? Probably about an RMSE or so. We're probably going to be, if we go up and down two of those, that's going to be about 11 days. So you take the trend line and say plus or minus 11 days is probably pretty likely to occur. If there is even a linear trend line, that is. Okay, so you tell me X, okay, and I'm going to do the plug and chug. So if you tell me X is 110, I can plug 110 into the equation and have 128 plus 110 times negative 0.07175. And here's the question. Is there any reason to think this is a little bit bogus with this data set? The only thing I could suggest is the following, and I have seen zero answers from students of this when I've asked this question across multiple different classes, like you guys in Stat 313 and Stat 252. Here's something that I can see if I talk myself into it. It seems pretty flat until we hit maybe 80. And then from 80, it seems to decrease, yeah? So I'd say maybe a flat trend and then a decrease. Maybe it's not really linear. That would be a great answer. But another student who said, looks pretty linear. Cool, I'm good with it. I'd be happy with that answer as well. So those are the actual midterm questions given 2 years ago. And the answers, I think I've built into then the not just the brief answers, but the full answers if you want lengthier versions. I'm happy to address any questions you have or any probability problems, especially those that were due last night by midnight from homework, because not everyone says they turn in the homework and felt immediately comfortable with it. Okay, so what I'm going to do then is say, cool, excellent. I want you to enjoy the next couple of days taking the test, and then note it's light stuff. Chapter 6, quality control, is pretty straightforward. Most students can read it and say, okay, I got it. Look for the pattern. And you do the lab, and we're all happy. And then you're ready for Monday's class when we move on into Chapter 7, more about statistics and inferential statistics in particular. So I'm going to sort of stop that, and I'm going to stop the recording in a minute if none of you tells me you want me to keep it going. But I'm just hanging here, doing nothing. And when I said I'm going to stop it in a minute, I meant, figurative, not a literal minute, and no one's even unmuted to suggest you have a question. So I'm going to stop the recording and